The S BAN: Insights into Shape-Changing Haptic Perception via Virtual Pedestrian Navigation. S BAN stands for Shape-Based Assistance for Navigation. In this work, we present a new haptic interface which communicates spatial information to users via their ability to feel changes in shape. The device is handheld and articulated, with a mechanism that enables its body to pivot left and right, in addition to extending and retracting. The S BAN is a unique shape-based interface in that it features a continuous two-dimensional workspace, which we utilize in this case to represent navigation cues. In this informal demonstration, an operator is using a laptop to wirelessly control the navigation cues provided by the S BAN. A volunteer who is holding the S BAN is then able to follow those instructions to be directed around an indoor space. Note that this demo is not part of our paper and serves only illustrative purposes. The S BAN is almost entirely 3D printed and is easy to assemble. It is an open source device allowing others to replicate or modify the system and build upon our work. Inside the S BAN is an IMU enabling orientation calculations and two linear actuators arranged in a parallel kinematic structure. Various inverse kinematic approaches can be applied to this configuration to enable different spatial to shape mappings. In this paper, we examine two kinematic mappings which use different parts of the S BAN as the control point. In the first case, inverse kinematic control is focused on the midpoint between two tactile notches on the sides of the device. In the second case, the control switches between the tactile notches themselves. When extension and angle are both zero, both mappings produce the same device configuration. For all other workspace locations, the different mappings lead to different device shapes. An LED array allows visual feedback for certain comparative experiments. However, this isn't used in this particular paper. To understand how well users perceive the shape feedback of the S BAN, we conducted stationary perceptual experiments, allowing us to map sensitivity over the device workspace. To evaluate our system in an embodied yet controlled experiment, we developed a virtual reality task where users must follow a dog to find buried bones. During the experiment, the user's head pose and movements in the virtual world are recorded. In some trials, the dog is invisible, and users must now follow them using either a virtual handheld visual feedback device, which is analogous to a smartphone, or the shape-changing haptic sensations of the S BAN. We also combine the two modalities in a separate condition. The results illustrated that participants were able to follow the dog with all feedback modalities. Although haptic feedback trials were slower than visual trials, participants' heads were more elevated with the S BAN than with visual feedback. This indicates that users were able to place more visual attention on the environment as they did not have to look at the navigation device. Reducing visual attention demands has positive implications for real-world navigation, where walking instructions on smartphone screens could distract pedestrians from the hazards around them.